If we focus our attention on a single molecule, for example a molecule of water, it quickly becomes clear that the idea of being inside it is misleading, because a molecule is not a solid object with an interior, but a stable arrangement of particles held together by forces. Each atom contains a nucleus, an extremely small dense region made of protons and neutrons. The protons carry positive electric charge and therefore repel one another. Yet they remain bound because the strong nuclear force operates at very short distances and overcomes that repulsion. Neutrons, which carry no electric charge, add mass and stability without increasing electrical forces. Even at absolute zero, these nuclei cannot be perfectly still. Quantum mechanics forbids exact position and momentum simultaneously, so zero-point motion is unavoidable, a direct consequence of the Heisenberg uncertainty principle. Surrounding each nucleus are electrons, but they do not orbit like planets. Instead, they occupy quantized states described by probability distributions. An electron does not have a precise location until it interacts with something. And even that interaction alters its state. In a water molecule, the oxygen atom draws the shared electrons closer to itself than the two hydrogen atoms do, creating an uneven distribution of charge. The molecule has a bent geometry, with a bond angle of about 104.5 degrees, and this shape, combined with the unequal sharing of electrons, produces a permanent electric dipole. That polarity is fundamental to Waals' behaviour. When light interacts with the molecule, a photon is absorbed only if its energy matches an allowed transition. Absorption does not push an electron along a path, but changes its quantum state, instantly redistributing charge and slightly altering bond lengths and angles. Chemical bonds are not rigid links. They are dynamic balances between attraction and repulsion, constantly vibrating. These vibrations occur in discrete modes, not continuously, and energy flows among them even when the molecule is isolated. When other molecules are nearby, additional forces come into play. Temporary fluctuations in electron density create transient dipoles, leading to van der Waals interactions. Individually, these forces are weak, but collectively they shape macroscopic properties such as boiling point, surface tension, and phase behavior. In water, polarity also allows hydrogen bonding, an interaction stronger than typical van der Waals forces but weaker than a covalent bond, enabling neighboring molecules to influence one another without forming permanent attachments. None of this involves direction or intention. It follows directly from charge, mass, energy, and the constraints imposed by quantum mechanics. Stability at the molecular scale does not arise from stillness, but from constant motion confined within narrow limits. A molecule persists not by resisting change, but because the ways it is allowed to change are tightly defined. What we are describing, then, is not an object in the everyday sense, but a continuously maintained physical pattern governed by interactions that operate reliably, predictably, and without interruption.